extraction is going to take a little bit of time. While that runs, I will be explaining what the product is actually doing. So this is LayerD Motion Studio. It is going to turn a flat design into a motion controlled video. The input is a PNG, but you can also use a JPG or a WebP image. The LayerD is going to separate that image into movable pieces. It's going to use a multimodal LLM, in this case GPT 5.6 Soul, to group those layers together, and then it's going to use remotion to animate those groups into a MP4 file. So we are using this image. So the core idea is coming from MGGen, which states that the motion is easier to control when the visual has explicit structure. Running the paper's original models and weights would be very expensive for this project. So I kept that core idea and changed the implementation. I recovered the layers from a flat image, add semantic structure to it with GPT 5.6 Soul, then use a deterministic motion preset. This gives the user direct motion and makes the result repeatable. So the user works in a Next.js application protected by Clerk. The authenticated API route sends the image to a local fast API service, where the LayerD is using Bitrefnet and Llama to extract transparent layers and inpaint the layers behind them. The result then goes into GPT 5.6 Soul, which acts as a multimodal LLM model. It sees the original image, a numbered contact sheet, and each layer's geometry. It groups the layers by meaning, such as by headlines, by products, by illustrations, or by background. The grouped SVG is then stored to Neon Postgres. Remotion reads the same SVG, applies the selected presets, and renders the MP4 in the browser. The process running now has two stages. First, LayerD reconstructs the image as positioned transparent layers. Then, the multimodal LLM decides which fragments should move together. The grouping step has two hard checks. Every layer must appear exactly once, and a full canvas background cannot be mixed with the foreground content. The group plan is embedded inside the SVG itself, so the saved project contains both the artwork and its animation structure. Now the design is reconstructed as semantic groups. The preview is frame-based, so the preset will produce the same motion every time. Now let me switch. I can switch between the presets immediately without running either model again. The text is kept separate from panels and illustrations, while pieces of the same illustration can move as a single unit. Let's click on this. The final export is a 5-second 30 frames per second H.264 video. Rendering happens in the browser itself through web codecs, so the video does not need to be passed through a render server. This is the rendered video. The browser has produced this H.264 video as a local blob. The video is ready to be previewed and looped, while the saved project remains separate in the database. Let's go over the history. Each extracted project is saved as a self-contained SVG. Reopening it will not call the LayerD and GPT 5.6 models again. It saves time and a lot of model costs. Let's open this. This row is stored in Neon Postgres. It contains a clerk ID, the clerk ID over here, and original file name SVG, project ID, and creation time. Queries are scored by user signed in user and including reads and deletes. The Python service loads the LayerD pipeline once at startup and reuses it across different requests. The conversion endpoint accepts the uploaded image, and returns the canvas, the SVG, the layer positions, and transparent layer images. The Next.js route uses the Vercel AI SDK with structured output. The model receives the source image, contact sheet, and geometry, then returns a typed group plan. Before that plan is accepted, validate plan check the layer allocation and the background isolation. The renderer reads the group metadata from the SVG. It calculates one transform per semantic group, staggers the entrances, and finishes on the exact reconstructed design. The motion stays deterministic because the model never writes the animation code itself. This hook connects the UI flow, conversion, project persistence, preset changes, compatibility checks, render progress, and the final browser object URL. The fast API logs confirm that the /convert requests completed, and the Next.js logs, they show that the conversion and the API requests. The render percentage is reported in the browser itself. And here are a few demos that I have saved. You can also see them in the README file. The main result is a working motion-controlled pipeline built around editable visual structure. It accepts a flat design, recovers its layers, organizes them by meaning, gives the user predictable motion controls, and exports a standard MP4. The repository also includes several inputs and rendered outputs, so the behavior can be compared across different layouts. You can see them. The left side is the original SVG and the right side is the final rendering. So that was it for the demo. Thank you.